طلعت معاكم الشاشة؟
يس اوكي تمام.
طبعا نستميحكم عذرا ان المحاضرة حتكون باللغة الإنجليزية نظرا لأن المصطلحات جديدة وكثيرة غالبيتها بتكون باللغة الإنجليزية، فنحاول ان نعطيكم انطباع خاصة لطلبتنا الموجودين في الداخل، ونتمنى ان يوم من الأيام يواصلوا دراستهم ويلتحقوا بالجامعات العالمية ويشوفوا اسلوب الالقاء والبرزنتيشن كيف بيكون في الجامعات العالميه، خاصه الناطقه والمتحدثه باللغه الانجليزيه. فمن الان الى نهايه المحاضره حتكون باللغه الانجليزيه. اذا كان في اي سؤال ممكن تفضلوا ويسالوني في اي نقطه في اي وقت من خلال القاء المحاضره. The title of the presentation today is going to be Increase the Performance of Wide Bandgap Perovskite Solar Cell via Surface Passivation, presented by Dr. Khalid Mshadi. I'm the Principal Qualification Reliability Test Engineer at Solaro Technology Incorporation. Also, I hold the title Scientific Researcher at Materials Engineering and Technology Research Group, METRG. As we go through this presentation, we're going to see that we're going to have some grasp of the introduction, background, previous work done on this type of solar cells. Also, we're going to explore the challenges, problems, motivations, objectives. And after that, we're going to see or introduce the term perovskite. What is perovskite? And after that, we're going to and after that, we're gonna go through the crystallography. نتمنى بس من الأخوة اللي يشاهدوا فينا يدير ميوت للميكروفون، لأنه يدير في تداخل. أعتقد أنه كان سؤال أو شيء زي هيك، فاللي يتابع فينا من فضلكم ديروا ميوت للميكروفون. So as we mentioned that we're going to go through the crystallography structure of the perovskite, experimental procedures, results and analysis. We're going to talk more about the characterization of these results and the analysis. And at the end, we're going to conclude whatever results and analysis we concluded in the presentation. My recommendation for the future works for the people that are interested in proceeding furthermore with this research, and acknowledgement. So as an introduction for this topic, we know that the renewable energy, one of the very famous renewable energy source is the energy from the sun. We call it like photovoltaics, one of the resources. So basically we turn the light that comes from the sun via solar panels to the electricity with some simple devices. And this type of energy is very clean, and it's utilized and it's endless. There is no end for this kind of sources. It's gonna last forever compared to the human lives. So why we go to the renewable energy? Why renewable energy is in much need right now? Of course, one of the main reasons is the CO2, carbon dioxide emissions now produced by thousands or hundreds of thousands of factories around the world. And this pollution increased the CO2 emissions from 270 parts per million in 1890 to 400 parts per million in 2015. So we need the renewable energy. Renewable energy is the main source available for energy since the creation, since the start of the human being or the life on the earth. And we have too many types of these renewable energies, such as solar, hydro, wind, tidal, geothermal, and biomass, and more. So now, specifically in this presentation, we're gonna talk about the photovoltaics. We call it PVs. Photovoltaics, as I mentioned, it's a clean energy, will not destroy our environment, will not produce any types of hazards to the environment that human beings is utilizing and use. Basically, the idea of the photovoltaics is to convert the sunlight to energy, to electricity, to power that we can use in our daily needs. So first, the photovoltaics effects was explored and noticed by Becquerel in 1839. And this guy in the, let me take my pointer here. And this guy, his name is Russell Ohel. He's the first guy that produces the first silicon solar cells in 1946. So the first existence of the solar cell was in 1946, silicon solar cells. Photovoltaics basically is a semiconductor device connected or made of two junctions. If you know the semiconductors, they connect of P-N junctions, where you have B junction attached to N junctions. P junction has the majority of the charge carriers holes. It's going to be holes. So we will call it hole transport layer or hole transport junction in the future, or HTL. And the other junction, N junction, since it has electrons, are the most majority charge carrier. We call it ETL, electron transport layer. So and the silicon solar cells, they have limit. They cannot pass that limit. They cannot exceed it, because theoretically, silicon solar cell, single junction, they have 30% efficiency. They cannot go beyond it. No matter what you do, it's going to be less than 30%. And nowadays, we have the maximum efficiency for silicon solar cells, single junction, is 26.6%. So this is a problem. We need a technology that we can produce more than 30% in efficiency. So which led the researcher to take a new path to look for new materials, specifically thin films, to explore the science and the branch of a new technology for solar cells. And that's why we introduced the perovskite to replace the silicon. And we're going to see why specifically perovskite is needed in this term to work in the solar cells. In general, thin film is more efficient in creating electric field at interface between two different semiconductors. As I mentioned, P and N junctions, they are very efficient to create the electric field between these two junctions. And if we have multiple junctions or multi-junctions, this device is we're gonna call it as a heterojunction solar cells. Heterojunction means multi-junctions. So one of the problems or the issues that we have in this kind of technology, the thin film solar cells, they have deep trap state density. It's a kind of traps that holds electrons or holes, and they reduce the performance of these solar cells. So these defects are found in the large numbers at the grain boundaries within the perovskite films, also found in boundaries themselves. And the main reason why we have such defects in the perovskite or thin film in general, because these kind of materials, they have a low formation energy. The formation of these thin films happens at low temperature. It's about 80 to 100 Celsius. To break it down for you, pieces that you would understand and you kind of classify the terms of solar cell technologies, we draw this type of schematic to specify or classify the solar cell technologies in three branches. One, you see here, it's a silicon technology, And the other one is the semiconductors compound. The last one is emerging novel materials and perovskite thin films. Some of the thin films technology is in there. So from this technology, this is all the technologies in solar cells. We have only two main categories. Solar cells made based on wafer-based, which has a red indentation. So single crystal silicon and multi-crystalline silicon, both are wafer-based. Also, we have gallium indium phosphorus, gallium arsenide, other technologies, they have wafer-based technology. On the other hand, we have thin film technology with blue dot. So, for example, cadmium telluride, copper zinc tin sulfide, and of course, we have perovskite and quantum dots, DSC, dye-synthesized solar cells, and other organics as a solar cell technology. So the main two parts is wafer-based and thin film-based. In the background about the perovskite solar cells, we call it metal halide perovskite solar cells, or PSCs. Is a very good example for the thin film technology for the solar cells in general, because they have very excellent optical and electronic properties, such as large optical absorption coefficient, high carrier mobility, and long carrier lifetime. Also, you will see through this presentation that perovskite, we can manipulate and tune the band gap of this material. We can change the band gap as we dope the material with different additives. So we can change the band gap to the purpose that we need. PSCs have shown very rapid progress. The first perovskite solar cells were developed in 2009, and the efficiency was only 3.8%. But after 11 years, the efficiency increased to 25.5, which is very close to the silicon solar cells. It has been about 80 or 70 years now. But perovskite did this improvement over only 11 years and is still under development. This rapid improvement is unique in the history of photovoltaic devices. Specifically, wide bandgap perovskite solar cells hold the promise of boosting the efficiency by extracting a portion of photo-generated carriers at a high voltage. So, due to the wide bandgap properties for wide bandgap perovskite solar cells, they're gonna absorb the photons. They come from the sun at a specific wavelength, and they're gonna transfer those photons to electrons and generate more photo-generated electrons or holes, and that added more efficiency to the solar cells. So PSCs will be used as a wide bandgap absorber material in the tandem solar cells. Tandem solar cells, this term means you have more than one cell and you stack them together, you connect them together. There are two ways, monothermically or mechanically stacking, to have kind of one cell with multiple cells inside it. And the purpose, we need to suppress the fundamental efficiency. We need to increase the efficiency. By the way, this technology have been used, and now it's giving the efficiency. Some of these types, they're giving the efficiency up to 46%. So way much better than silicon. So now we have some solar cells, they have 46%, which is way higher than single junction silicon solar cells. So the research have been done since then, 2009, and other groups, they done research as well to improve the performance. For example, Noah and his team, and Apron and his team in 2013, they started the search of tuning, changing the band gap for these materials. So they studied these materials, and they did tune the band gap from 1.5 electron volt EV up to 2.3 electron volts. And of course, if we change, as you study electrons, electronics, or maybe physics, if you have a background of physics, you know that if you change the band gap, you're going to change the wavelength for the absorption of the material. So let me give you an example. For example, silicon glass. We have the wide band gap. The band gap is about 1.2. That's why we see it as transparent. If we increase the band gap for the silicon, it's going to be darker and darker. So this is basically kind of given an information why we need to tune or change the band gap of the material to specify a specific wavelength for these rays or the sunlight to be absorbed. So as we tune the band gap, it's already opened a new type of tandem solar cells. In 2014, Wang and his team reported the beneficial effects of including additional lead iodide, PbI2, to the fabrication of perovskite solar cell. This addition passivates the perovskite films and leads to longer carrier lifetime. We need longer carrier lifetime to be a good solar cell. One of the properties that we're looking for, a longer carrier lifetime. A year after that, Zhou and his team showed that the deep traps or the deep states and the grain boundaries can be passivated, eliminated or reduced by adding fluorine type of material. We call it PCBM as an additive to the perovskite precursor. In 2015, another team, they reported the passivation process. So passivation process is the process that's being used scientifically to reduce the defects and increase the performance. They use the passivation process to reduce the ETL trap states, the electron transport layer trap states, and after that, they minimize the device hysteresis. The hysteresis and solar cell, this is a kind of term that hysteresis is a bad thing for solar cell. If you have too much hysteresis, that is very bad cell. If you reduce the hysteresis, you will have a good solar cell performance. In 2016, Ka and his team showed that spin coating method to introduce an ultra-thin fluorine layer on the top of the perovskite layer. And that helps to passivate the grain boundaries and make the grain boundaries more smoother. They will not be traps in between the grains. Haddadin and his team in 2016, they did the passivation for perovskite surface by adding N-doped graphene to reduce the non-radiative recombination. It was confirmed that the graphene was positioned on the top of the perovskite film, and we will see how we create the perovskite film and the experimental procedure. Now in 2016, in the same year, Yo and his team, they realized that the addition of lead thiocyanide increased the grain size. We need a bigger grain size so that charge carrier, they can move easily, freely, without any deep trap states. So because they did this, they introduced the lead thiocyanide, they increased the charge carrier lifetime, and the team was able to increase the open circuit voltage. You would see this term, VOC. Also fill factor for the solar cells and enhance the overall performance for this type of cells. Also, there was another research reported from Lee and his team about adding the Lewis-based material called caprolactam. Caprolactam has ability to reduce the charge recombination. Caprolactam is beneficial to passivate the perovskite grain and the grain boundaries. In the same year, Zha and his team introduced the BA, benzylamine, to passivate the highly defect areas such as grain and grain boundaries. And these areas were eliminated the trap states and reduces the VOC deficit. Also, there is team, they use cesium bromide, team, to treat and strengthen the contact between the two layers, the electron transport layer and perovskite interface. This treatment allows rapid photogenerated electrons extraction, resulting in high fill factor up to 80%. Fill factor, we need it high up. So when we have a good fill factor, we have a good performance. This is one of the characterization we use in solar cell. I'll show you later on the graph for fill factor and how does it look. A year after that, a group led by ZA introduced ethylamino alcohol chloride to the perovskite precursor. And the goal of this is using the hydroxyl group and the amino groups to improve the grain size via cross-linking agent. So they increase the grain size by using this kind of technique. Also, another group, they use guanidinium bromide into the precursor solution. The result was reduction in VOC deficits, which attributed to decrease of the defect density. So there are a lot of researches have been done and still under investigation. But from what I mentioned, what I summarized, we can see there are some challenges, some problems we have in this technology, new technology. So first thing that we have limits on the performance of single junctions, like silicon solar cells. One of the challenges is the accumulation of deep trap state defects in the grain boundaries due to the low formation energy. Also, another challenge, reduce the formation of interface defects into multi-junction solar cells to improve the hysteresis conditions. Increase the VOC, this is one of the challenges, to enhance the overall performance. Increase the grain size to increase the charge carrier lifetime. Motivation. So what motivated me to do this research and follow the research and do the experiment to see is that I believe that the use of different concentration of phenyl hydrazine iodide, I'll be calling it as PHII, as an additive is expected to passivate the wide bandgap perovskite grain boundaries, leading to greater efficiency. So we will have a better performance. Objectives and goals is to improve the wide bandgap perovskite solar cell, fill factor, VOC, and overall performance. And my goal was to increase it by 2% using this new material. So as I'm going through the presentation, we have mentioned the term of perovskite many times. So what is perovskite? Perovskite, the term perovskite was used to for the typical or the type of the mineral that was first found in Ural Mountains and named after the Russian mineralogist Lev Perovsky. This mineral is composed of calcium, titanium, and oxygen in the form of CaTiO3. So any chemical compound has the form of ABX3, it's going to be perovskite. And there are many chemical compounds, and perovskite family is so big, so broad, used in different areas. But now in this presentation, we're going to explore more about the perovskite which used in solar cells. This slide talks about the crystallography of perovskite. Perovskite lattice arrangement can be in many different structures. It has many different structures. It has a unique structure. There is no specific lattice structure you can tell this is specifically for perovskite. Different perovskites has different lattice structure, but this is the ideal crystallography can be presented for perovskite. So as you can see on this diagram here on the left side, we have three components, A, B, X, where A is organic cation. Usually we use methyl ammonium. We call it MA, or formaldinium FA. The next material is B, where it's a big inorganic cation. Usually it's lead or tin. X is a slightly smaller halogen anion. It could be iodide, bromide, or chloride. These are the halogens, or maybe a combination of 2 or 3 of them. There are a lot of researchers, they use only one, or maybe use 2, or maybe the combination of 3. As I'm going through the experimental procedure, I would like to introduce why we use the PHAI, phenyl hydrazine iodide. Phenyl hydrazine iodide has very unique characteristics because it's rich and it has the amino group in it. And some researchers, they mentioned that the amino groups, they have the super molecular interaction between hydrogen bonds and iodide, such as CHI and NHI. So basically they work, if you see those molecular, the hydrogen, the brown one is these moleculars, is basically hydrogens or ammonium groups. Okay, so they work to bring two grains, they are adjacent, they bring them together by some kind of force and bring them together and make one big grain. And we will see this in the pictures later on. So the amino group incorporate into the prophesied crystals and anchor to the surface of these grains. Because of this property, PHI is a good cross-linking agent. We use it to bring small grains and form bigger grains. What you see now, it's the final shape of the solar cell that I have made, and usually we made in the lab. So usually we start with FTO coated glass cleaning, basically 1.5 by 1.5 centimeters, fluorine doped tin dioxide, we call it FTOs. And we do some etching on the edge. If you see this edge here, where we have that silver finger, basically we etch that FTO for a connection purpose. So when we're done with etching with hydrochloric acid diluted in the percentage of 2 to 9 with DI water, we clean the substrates ultrasonically, an ultrasonic bath, where we use detergent, dionyzed water, acetone, and isopropanol. And each one of them is going to last at least for 25 minutes. Then the glass substrates were treated with ultraviolet ozone, UVO3, for 15 minutes. After we're done with the ozone treatment, now we're going to fabricate the whole transport layer, HTL. So we will take these substrates and put them in a spin coating process to deposit the B.PSS aqueous solution with the recipe of 5,000 RPM with the acceleration or ramp rate about 4,000 RPM per second for only 40 seconds. After we're done with this step, we will take the substrate and put them on the hot plate for a temperature of 145 Celsius for 15 minutes. And after that, we let them turn off the hot plate, let them cool down to room temperature. And it's the next step where we need to form or deposit the wide bandgap perovskite layer. Basically, this step will not be done outside or in the room conditions. We need to transfer the substrates inside the glove box filled with nitrogen and do the spin coating there. So once we transfer them to the glove box, we're gonna spin coating the prophesied solution. Prophesied solution was made the night before, and it consists of 143 milligrams of methyl ammonium iodide, MAI, and 184 milligrams of lead iodide, 220 milligrams of lead bromide, and finally 26 milligrams of cesium iodide. All these chemicals, they were dissolved in 1 ml of mixed solvent, gamma B and DEMSO, with a volume ratio for a 7:3. And the solution was stirred overnight at 70 degrees. Excuse me. In addition, we will make 4 conditions where we have 0, there is no PHI agent, or we have 1. These are the different conditions. We have 0, we have 1, 2, and last one is 3 milligrams per milliliter for the PHI. So now it's time to fabricate or deposit the perovskite layer, and we will use the spin coating techniques with 2 steps process. First, 2000 RPM with a ramping rate of 1000 RPM per second for 15 seconds, and the second one at 5000 RPM with a ramping rate of 2000 RPM per second for 45 seconds. These 2 stages, they're going to be, there's no stop point between them. So whenever the first one ends, the second stage is going to start right away. At the last 20 seconds of the process, the second stage, we're going to drop the 500 microliters of extra dry toluene. And this step is just to make the crystallinity of the perovskite film is more mature, more good, has more crystallinity structure. So the sample were after this deposition were annealed to 100 C for 10 minutes. So basically this schematic shows that we drop the perovskite, start spin coating the process 1 and 2. At the end, we drop the 500 microliters of extra dry toluene. And when the process done, the spin coating stops, we take the sample and put it right away on the hot plate. So after we're done with this, the samples were cooled down. Now it's time to fabricate the ETL, the electron transport layer. The solution of 20 milligrams of the organic material, PCPM, and a chlorobenzene solution was stirred overnight and used in this step with the spin coating technique again at angular speed of 2500 RPM with a ramping of 2000 RPM per second for 40 seconds. Also, we added rhodamine dye to the solution. Rhodamine has a good effect on the layers, so it's enhanced the performance, enhanced the crystallinity of these films. So we use that, and after we're done with rhodamine, we transfer the samples through, there is a channel from the glove box to the evaporator, thermal evaporator at high vacuum. It's about 5 × 10⁻⁶ millipar. And the reason we put it in the evaporator is because we need to put the connections from the cell to our circuit, which is, we call it silver electrodes. So now the characterizations of the solar cells. Some of the samples that when we're done with the perovskite step, we just take some samples for our characterization. We will not do the extra layers because we need to examine the perovskite layer. So as you can see here, they are a group of SEM scanning electron microscopy. And we have 4 conditions, as I mentioned before. We have 0, picture A shows 0 PHI, picture B 1, 2, and D is 3 milligrams per milliliter. From these images, we can tell that the biggest grains is in the condition where we have 2 milligrams per liter of that material, PHI. So adding only 2 milligrams per milliliter of PHI gives us a good condition where we see smooth surface and we will see bigger grains and the film, where the other three conditions, they are less than the optimal condition. So from this SEM image, we can tell based on the grain size, the third condition where we have 2 milligrams per milliliter is the best. So I tried to put some schematic describing why this happens. We see at zero smaller grains, but as we increase the content of PHII, we see at 2 milligrams per milliliter, a good grain size bigger. But as we added more, the grain size reduced, getting smaller and smaller. So first, when we added only 1 milligrams per milliliter, it wasn't enough to grab the boundaries, the grains together to form one big grain. But in 2 milligrams per milliliter, it was good enough to bring two adjacent grains together and form a big grain. If we increase the content of this material between the grains, that will not make a bigger grains because we have too much, more than enough, too much between the grains, and maybe we will not have these grains to come together and form the bigger grains. Continuous on the characterization process, we did the XRD. Image A or picture A shows that the XRD for the 4 conditions, as we can see, 0, 1, 2, and 3 milligrams per milliliters of PHI. And it was confirmed that we have prophesied films because we have this peak 100% at specifically at 2 theta 14 degrees, and the other peak at 28.4 degrees. So these two peaks are unique for the prophesied crystallinity, the structure, and it confirmed that we have formed the prophesied layer on the top. And these two peaks, the 14 and 28.4, related to the planes 110 and 220, respectively. XRD characterization shows that the narrow peaks, which support the enhancement of a crystallinity, when you have a sharp peaks, you would see that very good crystals in the material. Also, we have done the UV visible spectrometer, and this spectroscopy shows that the 4 conditions, and also we use V visible with a specific function. We call it taco plot. It's a procedure to calculate the band gap of the material based on the spectra of UV visible for the material. So no matter we change the content of PHI, we will have the same band gap for the material. So the enhancement did not change the band gap of the material. And this is exactly what we need. We need to have a better performance, but the band gap of the material stays the same. Also, this is a different characterization we use in solar cell research areas. We use IV characterization curves and JV curves. So in picture A or image A, we have all the conditions 0, 1, 2, 3, and you can see, or you can tell from the graphs, that JV curve is the best one. The highest one is the one with 2 milligrams per milliliter. Also, the graph B shows the forward and reverse scan for only 2 conditions, 0 and 2. 0 is the control. From now on, we will call it control cells. And 2, it's the good optimal condition. So I have forward and reverse scan, forward scan, reverse scan, forward scan, reverse scan for this cell, and that gives us this shape for GV curves. And from our characterization, we noticed that GSC increased, the current density increased from 14.17 to 16.12 milliamps per centimeter squared. Also, fill factor, FF, improved from 68.3 to 75.5%. This is a huge improvement. And also, the power coefficient conversion efficiency increase. So the efficiency increased from 12.16 to the highest 14.63%. So this is for the best cell that have been tested. Also, there is another characterization, we call it SPO, the stabilized power outputs, where you have a solar cell and you expose it to the light for a certain time. Here we use it at 200 seconds. And it gives the SPO for the optimal condition, 14.15%, but the control has way less than that efficiency, 10.6. Also, there is another term or characterization for specifically for solar cells or photovoltaic devices. We call it external quantum efficiency, EQE. This is basically in terms of converting photons that they are coming from the sun to electrons in the material. When the electron comes from the sun, it hits the material, frees electron, and the electron become a charge within the material. So we need to know how much electrons we generated by, for example, if we have 100, for sake of example, if we have 100 photons that hits the surface, how many of them they were successful to generate electrons within the materials or holes. The integrated photocurrent density of the control is and treated condition for the control and the optimal conditions were 14.6, 65, and 15.75 milliamps per by centimeter cubed respectively. And these are basically calculated values, and they are in agreement with the measured values. So we are right there. The calculated, the theoretical values in good agreement with the calculated values. So now I'm summarizing the characterization for these cells. I have 12 cells for each group, and we have 4 conditions, 0, 1, 2, 3. And this is the value for current density, the first column. The second one is VOC, open circuit voltage, fill factor, and the overall efficiency, power conversion efficiency. So from these diagrams, 1 or A is basically showing the current density. From the 4 groups, we see that group with the 2 milligrams per milliliter has the highest mean or average than the other 3 groups. Again, for the voltage, open circuit voltage, this group has a mean or average above the other 3 groups. If we go to the fill factor, the mean or the average of these groups, the 2 milligrams, has more average or mean to the other groups. And overall performance, where the efficiency is measured, this group has the highest efficiency among the other 3 groups, or compared to the other 3 groups. So one more step I did, studied that the relation between the grain size and the efficiency. Is there a relation between the grain size and the efficiency? This is what I did, the studied statistics here. So this table has the grain size for the different conditions, and also the last column has the efficiency. So we mentioned that the optimal condition is 2 milligrams per milliliter, which has the highest surface area, 2.88 micrometer cube, and the efficiency has the highest 14.63%. This diagram here shows the number of cells, the count of cells from 0 to 30, and the surface area of the cells. And this measurement was done by METRG software, where you have the image taken from SEM, and you measure the area for 30 grains. I did 30 grains for each condition, and I just to take the average and a good understanding of the the mathematics there and statistics. So I took 30 data points to make the experiment more efficient, and we have more data. And I did the box chart here. So it's still the same, just different representation. Box chart where I have the mean, the average, the highest point, the lowest point. You have all the points on that box there. So the area on y-axis, the conditions, different conditions on x-axis. So we see here groups where the optimal condition has highest surface area. Basically, this is the picture from that software. First of all, you need to calibrate the software where you have to measure exactly the bar scale here, and you need to make it specifically for that measurement. And you just trace the grains. And you draw this, and the software will tell you what's the area you measured. Also, again, here, you trace the grain, and you will have the software will calculate it for you and give you the surface area for each grain you measured. And I've done this for 30 times for each conditions, just to make sure that we have enough data. So the result, the control thin film, the solar cell without any PHI, has a surface area of 0.0436 micrometers squared, while the optimal condition, the 2 milligrams milliliter PHI, has a higher or a larger surface area, 1.785 micrometers squared. Also, there are many other characterization done on these samples. The one that I'm presenting right now is CAFM, basically is current sensing atomic force microscopy measurements. And this basically, this measurements and this, the left side of the slide represents 3 different areas, 1, 2, 3. And this is the corresponding current, 1, line 2, and line 3. So for line 1, the current sensing microscopy goes from one grain to the other grain. And as it goes, it measures the current over that area. And we see this dip here, it's corresponding the grain boundary. So this dip area, we need, or curve, we need it as small as we can, because this big area, it has more trapped states. So the left side represents 0 milligrams per milliliter PHI. We don't have PHI in this side. So for the 3 points, we have different values, but they are very high. But the optimal condition, we have the values. Again, we choose 3 points going from one grain to another grain, crossing the grain boundaries. And the value was much less than the value from the control cells. That tells us that we have improved the performance of the cells. We don't have much trap density between the grains. So the charge carrier can go very easy from one grain to another grain. Also, I did another measurement to measure the potential difference between 2 different grains. And this method, they call it KPFM, basically is Kelvin probe force microscopy. And it measures the potential difference between 2 different grains. And we need this potential barrier to be less. Okay, so the less potential barrier, less value is the better. So in this case, we have the average around 73 or something for 3 areas. But in the control, in the treated cell, we have the average around 40. Okay, so you can see nothing. There is no big dip in the curve. That means we have less potential barrier. Potential barrier, they trap the electrons. They will not let the electrons travel from one point to another point. They work like black holes. They get the electrons or the holes. They will not move forward. So another measurement, which is very important in solar cells, we call it MS, Mochotsky plot, where the Mochotsky plot basically is measure the potential, the built-in potential. Cells with high potential, VBI, potential barrier or built-in potential with higher values is having very good charge transfer. So in our conditions, we see that the control cells, they have 736 millivolts. On the other hand, we have the treated one, 770 millivolts. Also, we know that heterojunction solar cell with a higher VBI have a greater electric field, and that boosts the charge transfer. Another measurement is basically represented in shape B, EIS, the electrochemical impedance spectroscopy, and this gives the resistance with the material. Measures the recombination resistance. The higher is the better, is good for the cell. So the treated cell has 22.1 kilo ohms versus 11.7 kilo ohms in the control cell. With higher recombination resistance in the treated device indicates that lower charge recombination and efficient charge collections. This is on nanoscales, talking about electrons and holes within the material. In my conclusion, summarize the work. An effective passivation method was established for engineering inverted planar wide bandgap perovskite solar cells by perovskite precursor doping with phenylhydrazine ammonium iodide. Improved fill factor, VOC, are results of reduction in trap state densities. We have less because of this treatment, and that's why we have we reduce the non-radiative recombination of photogenerated carriers and enhance the charge transfer from one side to another side. Better charge extractions through the interface and better performance. So as we added PHI at the optimal condition, we have improved the efficiency to the treated one 14.15% compared to the control cell. It was in this experiment 10.7%. So it's a good improvement, about 4% difference between the two conditions. Future work. What I suggested, if there is somebody interested in this work and need to proceed, there are different materials we can use. Actually, I haven't done this research, but I'm suggesting that if somebody needs to take the lead and do this research, they're gonna use BCP and C60s. They are fluorine-based carbon to the cell as electron transport layer. Also, through my experiment, I noticed that the thickness of the layer, perovskite layer, matters a lot. So I would recommend somebody to take the lead and change the thickness, maybe increase the thickness of perovskite. The perovskite that I worked in, they have a thickness of about 100. It's 100 nanometers. It's very thin. Also, this strategy demonstrated in this work can be adopted for perovskite from other materials, for other different kind of perovskite solar cells. We have a lot of variety of solar cells, and we can use this material in that application. Acknowledgement. I would like thank you, my advisor, Dr. Quinn Chow, and Center for Advanced Photovoltaics, and the Electrical Engineering Department at South Dakota State University. These are the references that I use in this presentation. Feel free to ask me for the references. They have done this work or the previous work and show some significant improvement. And I have ended my presentation. If you have any questions, please let me know. Thank you very much.